It's one of the worst parts of New York right here. I've seen a whole bunch of stuff, man. You know what I mean? But it's the streets.
Good morning,
you know what I mean?
everyone.
It is what it is, man. I'm born here, raised up here. You know what I mean? I ain't going nowhere. I love it here. I love it here.
Okay, well, congratulations on getting assignment 1. I can see you're all a bit tired from it, which is completely reasonable. How did it go? Is that better? Yep, I can see. Yep. Yep, okay. So I just asked, congrats on finishing assignment 1. And how did it go? Stage 4 was brutal. Yeah, okay. But I mean, the good part of it is that, that's only just one small part of the assignment. So that's completely okay. I just started sneezing a bit, so excuse me, I should settle down in a second. But yeah, that's okay. But first 3 stages went well then, it sounds like. That's good. I'm just scanning the chat really quickly. Yeah, we got heaps of emails, so I'll get to my emails as soon as I can. If you sent an email like a few days ago and I haven't replied, I've probably missed it. But yeah, it is better to email the course account rather than me personally for things about the assignment and stuff like that. Has the stream started yet? Yes. Okay. You feel confident with arrays and structs now? That's good. Yeah, awesome. I mean, that's the point of the assignments, right? They're not just there to hurt you. That's exactly what they're there for. So that's really good. Cool. Well, I can tell, yeah, everyone's pretty exhausted from the assignment. That's okay. We're going to give you a few days, I know it's not much, but a few days off before we release assignment 2. And when I say off, I mean watching the lecture and learning the new content that you'll need for assignment 2. So now a lot of the stuff that we've been talking about in the last few lectures, like the linked list stuff, the structs and the pointers, that's all going to be where we apply it, is assignment 2. Yeah. I think there is a function line maximum of 80 characters. Yeah, flexibility week is flexibility in getting your work done. It's not flexibility in, a holiday. Yeah, that's right. Excuse me. I don't know what's going on. Okay. Yeah, that's right. But you'll get there. You'll get through it. Okay. Are there any admin questions with assignment 1? So, taking a little step back on the admin, assignment 0 results were released. If you've got any issues, just email the course account, cs1511@cc.unsw.edu.au. I'm going to sneeze again. I don't know what's going on. Okay. So yeah, assignment 0 results released. That's all good. If you've got any issues, email the course account. 100%. Congratulations. That's really good. Hopefully you get the idea that the real purpose of assignment 0 is just to prepare you for how assignment 1 works. So if you had any big issues with assignment 0, hopefully you figured them out, and then assignment 1 you actually got it sorted. Assignment 1 you've submitted, we'll start marking those really soon actually. And then assignment 2 will be released either late this week or late this week, or maybe on the weekend or something like that. So a couple days off, but not really off because you'll be thinking about today's lecture stuff. So because of that, I'm going to try and take today's lecture ever so slightly slower pace, do a bit more of a recap because we had the flex week, so it's been a little while. So do a bit more of a recap from what our last lecture was talking about. Who can remember what we were talking about last lecture? I know you probably all struck it out of your mind because it wasn't required for assignment 1. Now, while actually you do that, I've just realized something. Give me a second. Just realized something I have to tell you all. Yeah, exactly. We just got started on linked lists, so structs and pointers and nodes, but we didn't really, if you remember, we didn't really get into it yet, and a few of you were really keen to. Okay, I've got this slide I need to talk about. This is an odd one for me as well. Sort of. Let me just move my camera here. So, let me see. What do I need to say here? Alright, so basically what I've been told, as far as I know, there is some precedence to an issue of some foreign governments directly or via proxying engaging in harassment, intimidation, or surveillance to suppress expression of views at UNSW and potentially with UNSW students, so people that, like yourselves, watching the lecture right now. It could manifest in threats, fake accusations, reporting, or threats to report behavior to foreign governments, and improperly sharing private information. We've seen instances reporting behavior and opinions of other students to foreign diplomatic missions, which can be intimidating and things like that. So all I'm trying to do now is just raise awareness of this. If you think something like this is happening, basically the university has ways to support you and process help you through the situation. So you can respectfully disagree about anything, express different opinions, write your beliefs, show your beliefs, leave any club or organization. I mean, that's interesting. Yeah, I don't think it's meant to be scary. I mean, it's okay. I'm sure it's a very small percentage. And I don't actually think in computer science we get maybe targeted on this sort of stuff because we're not a very political field generally, but not always. But so yeah, it's not okay to... I mean, this is just good general advice anyway. Censor others, use hate speech, threats, false accusations, or share private information. What can you do if you're seeing something that's a bit... if you don't know, quite what's going on, if you're not 100% sure about it, you can tell me, someone like me, your teacher, your lecturer, your tutor even, but they'll probably report it to me. We have the psychology and wellness team at UNSW that you just get free access to. UNSW complaints, maybe if it's coming from an academic or something like that. UNSW security, so they're trained to handle it. And of course the police. And there's a QR code there to scan to find out more. Okay, any questions? Not that I know. Yeah, I'm not meaning to scare you, but... Okay. We don't deal with social issues? Well, we actually do. We do. But maybe it's not as obvious as other contexts. I mean, there's a huge, I think, growing opportunity for people like computer science and artificial intelligence ethicists. What's happening with Google's Lambda and is it conscious and all of this stuff. Where do we draw that line? What does that mean? There's some really interesting stuff happening, related to social issues, especially with artificial intelligence. So, yeah. Okay, are we ready to... Yeah, are we ready to do a recap? Let's do a recap. So we're doing linked lists. And if you remember last time, we just were creating head elements. So to recap that, let's just go back to here. Okay, let me fix this up a little bit. Okay, no. Oh, of course. And I want to gedit. What was the file? I guess it was intro linked lists. Yeah, this looks right. Okay. And I'll put this here. Okay. Can we have dark mode for gedit? Well, actually, on that, I was wondering if you would all mind if I switched to not using VLab for the lectures and using my local development environment. What do you guys think? Is it helpful seeing me do the development in the same environment that you work in? Or do you... I think it's week 7 now. I think you get the hang of it. Yes, you don't mind? You don't mind? You don't mind? Yeah, I use VS Code, not Atom. Maybe for the second half of the lecture, we'll switch. For this, we'll just... I'll stay and then we'll do the big reveal after. Okay. Yeah, Atom's dead, guys. Atom's dead. I think it's officially dead. Anyway, okay. Recap. It's all right. We're taking today's lecture a bit slow because of the assignment one. All right. So how did we get to this point before we even talk about this code? How did we get here? What's going on? Well, we had structs, right? Structs. And structs are collections of... how do I turn on dark mode? In gedit. File, where's preferences? It's under appearance. Yeah, but where's appearance? I shouldn't, oh, there it is. Edit preferences. Editor. Fonts and colors. Dark. That looks nicer. Is that still readable though on the lecture stream? It's a bit grayscale. Much better. Yeah, this will do. This will do. We'll switch it later anyway. Okay, better. Okay, cool. Okay. All right. So how did we get here? We have this idea of structs. A struct being, if to refresh your memory, a collection of memory or variables or data in a single thing. So it's something that we can define our own data type, like a node here, that can store an integer and can store, other things, a character, a float, another custom data type, an enumeration, whatever it is. So we have these structs, right? And the structs are useful. Why? Because we can store these collections of things, pass them around as a single container, a single group. Rather than having to pass in maybe, 8 separate parameters to a function, we can just pass in a single struct and we can write functions that know how to deal with that particular struct, right? So we have structs. The other thing we have is pointers. And what do pointers allow us to do? They allow us to do a few things. They allow us to pass a reference to a big piece of data or any piece of data so that we don't need to copy the value every time we pass it into a function, right? Because normally, if I call a function here, for example, this int data, the value gets copied in memory. So there'll be 2 integers in memory now. And if I do something in the function, it won't affect the first one because it's a complete copy of the value. That's fine, but that means if we have a big piece of data, for example, a big struct, that entire struct will get copied. And that can be an expensive operation in memory, right? So what a pointer lets us do is say, well, rather than pass in an integer exactly, copy the integer and go ahead and do that, I can pass in a pointer to an integer or a pointer to a node, a struct. And this will pass in the memory address to that particular integer. And then I don't need to copy the actual value in memory. Does that make sense? So that's one of the big things we can do with pointers. There's a lot of other things we can do with pointers. That just happens to be one of them. But pointers essentially allow us to handle, just like any integer or character or double, we can handle and manipulate and pass around references to memory, pointers to memory where we are storing that data. Okay. We can combine these 2 things, so we can have a pointer in our struct. All right, makes sense. We can put anything in our structs, really. And once we do this, and we make something called a node, which is just what we call some struct, which has some payload, some data. It doesn't have to be an integer, could be anything. Could be another struct, right? And we can chain these structs up by also storing a pointer to yet another node in the node. Does that make sense? And what this allows us to do is make a list of nodes that are linked by this pointer. And that's the introduction to linked lists. Is this coming back to everyone now? Yep. Well, one person says yep. Slowly? Yep, that's okay. So let's have a look at this little program here that we just had to get started. All this program can do at the moment is create a new node. What does that mean? That means it can initialize one of these structs. Let's have a look at how we do that. It's down here. I can't scroll it, unfortunately, but that's okay. Okay, that was just some stuff. Okay, a function that creates a new node. The node is a struct. It returns a pointer to a node, and its parameters is the data and the memory address of the next node. So these nodes, right, need to exist after the function is created. Therefore, we need to allocate these on the heap. The way we do that is with malloc, right? So that's one of the building blocks here. So we create enough memory for a struct, for a node, and we assign that memory location that gets allocated or generated to this new node function. We then set the data to be the value that we passed in, and we set the address to be we set the next address to be that of the one that we just passed in as well. And then we return that new node. Now, what are we actually returning here? Are we returning a struct? Or, yeah, exactly right, Nicole. We're not returning a full copy of the struct. We're just returning a pointer to where that struct exists on the heap. Does that make sense? So we return that address from create node. Here we're using create node. So in main, we're setting up our linked list, or just about to. We create the very first struct node pointer. We say create the node. Well, this should be 3 now. And what we do when we construct it like this, we're creating the node backward, the list backwards. So we start off with the final node, because the final node we know points to nothing. We have nothing to point it to, right? Then we hook up the second element, and we say that you point to that third node, the node with the value 3, and then we do it again. We point the first node to the node with the value 2, and down we just made a linked list. And the linked list will be value 1, value 2, value 3, pointing to each other, with the final node pointing to null. And if you remember in the last lecture, I drew that out. I can draw that out again if you would like. You guys let me know. But actually, this is a very small file, only less than 40 lines, because there's a lot of comments, and we've already actually initialized and created a linked list here. We're just not able to do anything with it. Yep, Polkabot, we actually construct a linked list with the opposite order we would fill it in. That's exactly right. In this case, because we need to pass in the next address, we're creating it backwards. But there's other ways we can do that. A drawing would be helpful, absolutely. In fact, I could also... Seems slow. Okay, let's do a fig jam. These are pretty fun. Seems really slow. Don't know what's going on. It's drawing time, exactly right. I guess because I'm streaming, maybe it's making it slow. Okay, can we see? I guess not. All right, and then maybe I'll just go over here. Yeah, you could always revisit the previous lecture, but I don't think there's any problem in, whoops, in spending some time. Oh my God, doing it. All right, okay. So what are we doing here? So let's start with main. Let's execute the program just as if, we are executing the program. So we start with main. We declare a pointer to a node. So we have this pointer here. Now, it is still a struct. It's a pointer to a struct. That means we have the data, but we don't have any value in, and we have the next, and we don't have any data in it. It's just an empty, well, it's just a pointer to the node, but we'll do it like that. On line 20, we create a node with the value 3 and point to the null pointer. Okay, so we call create node passing in 3 and null. So create node over here calls malloc. Well, this is just a pointer. So we call malloc here. We generate the actual memory allocation for the data. And then we say new node.data is equal to data. So we pass in the value 3. So the data is going to be 3. This isn't quite right, actually. Let me do something here. Whoops. Let's do like this and like this. Let's get a bit fancy. This is main. This is the heap. All right. We make this pointer here. This is a head pointer. Okay. Then we jump down here. We call malloc. We make the actual node itself in memory somewhere. And then we say, okay, the data is 3 and next is null because we passed in null to this address here, and we assign address to next, and then we return the memory address of it. And that memory address gets assigned to head pointer. So this head pointer is a pointer to this node. And maybe I'll just do this. What's the difference between the stack and the heap? The stack is the memory, the region of memory allocated for functions. So each function gets its own stack frame. So when we start main, basically the program gives us a bunch of memory that all of our variables will exist on the stack frame. If we call malloc somewhere, that's memory that we can allocate on the heap. The heap can exist throughout different functions, and it doesn't go away when the function ends. Whereas if main ends, obviously if main ends, the memory goes away. But if I have another function and that function ends, I'll lose the stack frame, but the heap will exist. I've covered this sort of in a lecture. Okay. So any questions just on that so far? So here we just have a pointer, right? Here we have allocated the actual bigger piece of memory that can store our data and the next pointer. This is our struct. All good so far. Perfect. Okay. That was line 17. Now we do line 20. So we do what's on the right first, always. Why no free? Because we don't want to get rid of anything yet, Elven Seed. There's nothing we wanted free. We want this memory to exist still. So on line 20, on the right-hand side, we call create node again. Okay? Sorry, line 21. Sorry. We call create node again. We pass in the data 2, and we pass in this head pointer value. So we pass in this memory address that it's pointing to, because head pointer is pointing to this. So we come down to create node, we pass in the value 2, we pass in this pointer, we malloc another struct, right? So another struct, another struct gets created. We assign it the value 2. Now next gets assigned the position of head pointer, which is pointing to this. So next is actually a pointer. Let's just do something like that, which means it's got an arrow pointing to here. Like that. We return new nodes memory address, and that memory address gets assigned to head pointer. So head pointer no longer points to that piece of memory or address, it points to this address. Does that make sense? Maybe we'll do this like this and this like this. Yeah, that's right, Bubbling, yep. Okay, and that is line 21 complete. And line 22 does the exact same thing one more time. So we pass in the value 1 and that head pointer. What's head pointer pointing to? Head pointer is pointing to this address here. So we create a new node. I might just make this a bit bigger. Create a new node, right? There's no data in it yet. The data is going to be 1, because that's what we passed in. And the address is going to be the address of head pointer. Head pointer is pointing to this position, therefore, therefore, this will now point to here. We return the address of new node. This is new node. So this address gets returned and assigned to head pointer. So this no longer points to this value and points to this address here. And then the program ends. So this is the final linked list. So that means main has a pointer that points to an element, and next gets assigned, something like that. So main has this pointer that points to a piece of memory on the heap that has a data of value 1, and it has a memory address. If I follow that memory address, I get to this pointer. This pointer points to a node, which has the data 2 and a pointer. If I follow that pointer, this pointer points to a node, value 3. If I can't follow its pointer, it points to null. This is my linked list. The list is linked by these pointers, and they're separate pieces of memory. So this could be somewhere here in memory. This could be over here. This could be over here. It doesn't matter. The reason this is beneficial is because it's easy to manipulate the order 100%. So you can imagine that if I wanted to put a node in the middle here, I would just have to rearrange the pointers. I wouldn't have to do anything drastic. Whereas with an array, arrays work differently because they are big, long pieces of memory. If I want to make it bigger, I need to move it somewhere I've got space and then, get a bit more data. But linked lists, they're not contiguous, so they're sort of scattered throughout memory. Let's just make this a bit nicer. Okay? That's exactly right. Exactly right. We can manually insert a new element at the end or in the middle or at the beginning without shifting any other element. Absolutely. Absolutely, 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 absolutely. Polkabra, 100%. If we print head pointer, it will print the memory address of this node right here, whatever that might be. We don't know what that would be, but it would print the address. We'll talk about inserting nodes, Nickel, in probably this lecture. Linked lists are arrays in Flex Week. That's funny, yeah. If I wanted to modify the order of the elements, how do we edit the program? We'll talk about that as well, don't worry. So head pointer is basically a guide for the other nodes. Head pointer is just our reference to where our linked list starts, right? It's just the address of the first element in the linked list so that we have a reference to it. Okay, all right. It sounds like we're all excited by linked lists, which is really cool. They are exciting. They solve, I know I mentioned this again last lecture, but they solve the big problem of arrays. The big problem with arrays is that if I've got, I just sort of said this, but if I've got this big array here and I want to insert an element and my array is full, I can't do it. I need to make a new allocation, bigger than the size somewhere else, and then I can put the new element in. It's really, anytime we copy or allocate memory, that's expensive. Linked lists help us because we don't need to, if I want to add to this linked list, I just, allocate a new block for that new element somewhere else. But there's downsides to it too. So linked lists aren't random access. We'll talk about that. All right. So just like magic, Polkabra says, so if we were to print the elements of the list, what would we do? Or why don't we do that? Why don't we do that right now? Does that sound good? So how do we print? With an array, I can just have a loop. I loop through, I print to each one using the index, and I'm happy. How do I do that with linked lists? Okay. Clear. Let's clear that. Let's get a nice little reset going. Blah, 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 blah. Okay. Oh, now, what have I got to do? Give me a second here. I got to move intro linked lists to week 7, and I'm going to call it linked lists.c. I need to then move into week 7 and gedit linked. Oh, I shouldn't have moved it. I've got to copy it back now. Sorry about that. Intro linked lists.c. Okay, copy that over. Now it's still here. This is fine. Gedit linked list c ampersand. Okay, close that. Close without saving. I probably should have saved it. That's fine. Save this. And then I've really just got to quickly go chmod so you can all get access to it. Clear the terminal. All right. So we need some way. We have already made a linked list in our program. We're just not doing anything with it. What we want now is some way to print our linked list. So we're going to have a function to do this, obviously. Now, if we're printing something to the terminal, we don't actually need to return anything. So our function's not going to return anything. It's going to return void. What are we going to call it? Print linked list is reasonable to me. Now, what does our print function need to accept as its parameter? Well, it doesn't need to accept any data because it's not doing anything to the linked list other than printing it. So it just needs to accept the address of a node, to start printing from. Now, could we call it something better than address? Yeah, we can call it the head pointer. We'll just call it the head because we know it's a pointer from the type. And then the semicolon here. But we can call that, we're just naming the variable here. But that's basically the signature for the function that we need. We can come down here, create node. We can do the printing underneath it. We'll paste that in. We'll open up a pair of brackets. And let's sort of describe what it is that we're doing here. I don't suppose I can collapse those, no. All right, so a function to print a linked list will need to traverse. We love fancy words like traverse, don't we? We'll need to traverse the linked list, printing each node's data value. It's nice to say it returns void. So it's a procedure, and its parameters are a pointer to a struct node. All of the 1511 recordings are on the YouTube channel. Exactly, thank you, Noah. Okay, it's really annoying that this is so close to the bottom. But what can we do? Well, actually, I know what we could do. We could do that. Okay. So, here's the problem with, well, not a problem. Here's the thing with linked lists. Let's get back our diagram for a second. If I have, once again, I keep drawing this array. If I have this array, that doesn't help me. If I have some array here, if you remember, all the elements are sequential. So if I want to access index 1, I just can read this value. Like I know where it is. With linked lists, we don't have that, right? I don't know where the second element's got to be. For me to know where it is, I need to have a previous element that points to it. Does that make sense? So arrays are randomly accessible, linked lists are not. So we can't use like an index to access the elements in our linked list. So if we think about what we need to do, let's think about what we have, right? We have this pointer to a node, and that's it, actually. So we have this pointer to a node. So we need to access that node and look at its next, then we can print out its value. So why don't we just do that? Why don't we just print out the current node that we pass in value, right? So we can say struct node current is equal to the value that we just passed into the head. So we assign our new pointer, we're just going to call it current to head. And then we can say if current is not equal to null, right? So if it's not empty, we do need to check that. Why don't we just printf? Now our data is a we're printing an integer. So we'll do that \n, comma, and we're going to print the current. Now, if you remember, when we've got a pointer to a struct and we want to access a member, we can use the arrow operator. Do we remember that from last lecture as well? And we can print out the data being the integer that's in the node. Oops. Do not disturb. That's in the node, semicolon. Okay, so that should just print only the single node. Oh my God, that's not going away. Okay. All right, so then let's go over here, and why don't we print, which node do we want to print? We can print any of them. No, we can't. We can just print, oh, we can, we just put it where we want to print it. So we'll just print the node with the value 1 down here. Print just the node with value 1, because that's what a head pointer is going to point to when we call print linked lists. So DCC linked list.c dash out to program. No errors, that's really nice. We print that out and we should just see the number 1 printed to the terminal. Exactly right. If we want to print number 2, we could put it here and we should see number 2 and then number 1. Okay, that's all making sense, right? So this function's currently just printing the node. Any questions on this so far? Yeah, so at this point, head pointer was pointing to the node with the value 2, so that's what gets printed. At this point, head pointer is pointing to the node with the value 1, so that's what gets printed. Is there a way to print all the elements at once? That's what we're going to expand our function to do. But I just wanted to do that there. So if you put another one, you get 3. No, it depends where I put it. So if I put another one here, what am I going to get? Three doesn't point to null. 3 points to the node with the value 3. Its next value points to null. Why does it print 2, 1, and not only 2? It prints 2 because at this point, head pointer points to the node with the value 2. Then head pointer changes to point to the node with the value 1. And so it prints value 1. It's just printing what the current head pointer is pointing to. So this will do 2, 1, 1, for example. Cool. Why does the position matter? The position of the print function? Because it doesn't, but it's just taking in the head pointer. Head pointer points to a node with a value, and it prints that value out. That makes way more sense. Okay, cool. Yep. Okay, so let's undo that. Now, this isn't too useful. I mean, it's not useful, but it's not... We want to print the entire linked list. I think that's what you're all telling me, right? We want to print the entire linked list, not just a single node. I mean, that's sort of useful. And the way we do that is actually fairly simple if we think about it. So, and maybe what we'll do is go back to our diagram here. At the moment, yeah, it's only printing the element it gets passed in, the node that it gets passed in. It's not changing it. So let's delete this. Whoops. Delete that, delete that, delete that. So we pass in head pointer. That's what we pass in here. We get another pointer to head. We check that it's not null, and then we just print head pointers data position with a value of 1. That's what this arrow is doing. The arrow is saying follow the pointer and print out data. You'll see why we have the current equals head in just a moment. Okay. So what we want to do next is we still want it. So that's correct. We want to print out data. Then what we want to do is follow next and print out next data. So the way we can do that is by saying, well, instead of just doing this if the current is not equal to null, we can make this a while loop, which is still doing the same thing. Like a while loop still checks this condition. While the current node is not equal to null, we print it out. But then what we can do is say, well, the current now is going to change, and it's going to equal the existing current's next address. And that's it. That's our printer. It's that simple. So let's run through this. We pass in head pointer to the function. We say, is head pointer not null? Correct, it's not null. It points to this value here. Okay, print out the data. Okay, we print out the data. Then, so actually we should do this properly. We have this current here, and current points to here. That's what we're doing on line 50. Current points to head pointer that got passed in. So this is line 50. Is current not null? Current is not null because it points to head pointer. Therefore, print currents. This is not quite right either. Current points to, whoops. Current is assigned the same address as head pointer. So it's more like that. Whoops, that didn't let me do it. Doesn't like me doing that. Something like that. Okay. So is current not null? Current is not null, that's correct. Print out current's data, that's 1. And then set current to be current.next. Next is 002, which is the pointer to this node, so it's just going over here now. And then we repeat. Is current null? Print out the data, point to the next. Okay, we point here. Is current null? Node, points to this one. Print out the data, point to the next. Next is null. So at some point, remember, null is just a special pointer somewhere in memory. So we point to null. And then we say, is current null? Current is null, and the function will end. And that's our printing. So we can compile this, run this. Oh, are we actually calling it? No. Now we can print all elements in a linked list. We call print linked list. We pass in the head pointer just the same. We can delete this, save that. We compile this here. We run it, and then we get 1, 2, 3 printed out. Yeah, you're all jinxing each other. That's it. This function prints out all elements in a linked list. Now that you kind of get linked lists, they are so cool. Yeah, they are really cool. They really are. Yeah. I mean, I don't know what to say. I mean, this is... I was just thinking something, actually. What would probably be nicer is to actually separate this into two functions. One being traverse linked list and one being print. But this is fine. This is fine. Okay. Let's do a quick poll. Not an official legal statement of the list. I can do another run through with the diagram for the print if we want. Or if you're happy with it, we can have the mid-lecture break and then talk about some other stuff. The logic makes sense. The code is you're unsure about. That's okay. The syntax will come. You've got to just spend some time writing the code. If you write the code, you'll be okay. Yeah, and you'll write it in the labs and things like that. Exactly right. Exactly right. Okay, let's see. 52% say sorta, I'll get there. That's completely reasonable. 42% say that they're okay with it, and 5% have no idea. All of it, this is all valid. You know, that's completely reasonable. Even if you've got no idea, it'll come to you to spend some time on it, writing it yourself. Elizabeth says, can linked lists in C be made any other way than with structs? Could we use an array of size 2 pointers? I mean, I suppose you could do it with just... You could do it without structs, but you would really not want to, I don't think. How can we practice at home without doing the labs in advance? Polkabrat, just recreate the lecture code yourself. Try and write the lecture code. Don't just copy, don't just copy what I'm typing, but try and understand it. Can someone please remind me what the style of new node to data represents? Whoops. Over here. Here. Oh, what the arrow means? Is that what you're asking? The arrow? Oh, right. Okay, does it mean pointer to new data equals... It's doing a few things. So the arrow dereferences the pointer and then access the member of the struct. And then it's just assigning that data to that data. Justin says, just a question, why do we need to create a struct pointer and not just a pointer? Good question. It is just a pointer, but in C, our pointers generally need to know the type of the thing they're pointing to so that they know how to dereference it. For example, here, if it didn't know that new node was a pointer to a struct node, how would it know how to interpret the data to access the member? So it needs to, just as if we have an integer, we need an integer pointer so that the program knows how to access and deal with the data that the pointer is pointing to. Cool. All right, let's have a 5-minute break. I might make another coffee. There's no Kahoot today. It's really hard to make them for linked lists because you need to have a lot of code. So maybe we need to think of some other mid-lecture. Does anyone have a good trivia question or riddle or something like that? Trust me, they wouldn't be fun because it would just be lines and lines. Maybe I could figure something out for tomorrow. I need a bit more time though, because usually actually I just whip up the Kahoots right before they run. And I've got to set up my local development environment. Yeah, too much code reading. Exactly right. All right, let's have a bit of a break. We'll come back and we'll do some more stuff. Let's zoom this in. Welcome to Visual Studio Code. So this is my local, in fact, let me turn this off. This is my, so basically this is instead of VLab, and then using gedit and stuff like this is just running directly on my Mac. You do not need to change anything that you're doing, right? You don't need to do this. You can if you want to. There's some limitations because it's not as simple to get DCC running on your own machine. So I'll just be using GCC, so that's okay. But yeah, basically this is just for me, not for you, if that makes sense. To break down what you're seeing on the screen a little bit. So VS Code, this is Visual Studio Code, not Visual Studio. VS Code is one of the best things Microsoft has ever made for developers. The biggest problem with it is what they named it, I think, because they named it Visual Studio Code. But it's not a big IDE like Visual Studio, although it's sort of getting there. But Visual Studio Code is like gedit. It's a text editor. So I've got a file called linkedlists.c open. It's a text editor. I can edit the text exactly like gedit. The difference is, one, this is just running locally on my Mac, not in I'm not VNCing in or SSHing into a machine. The second difference is it's a lot more extensible than gedit. So one of the things it's able to do is put a terminal, right, into the editor, into the program that's running the editor itself. So this is my terminal that I can compile my programs with, just like before I was doing it with, here's my terminal in a separate program to my editor, right? Here it's in the same program, which means I can minimize it, bring it back, and do stuff like that. But really, absolutely nothing is changing. Here's my terminal. Here's my text editor. I can compile linked lists, out to a program, and then I can run that program. And this is the exact same code that we just had on VLab. The only other difference as well is that instead of using DCC, I'm using GCC because I don't have DCC installed. Can you use VS Code offline? Yeah, absolutely. I mean, there's no internet connection required to compile a C program as long as you've got everything installed. So I could disconnect my internet and keep compiling and keep working. In fact, I've written many, many lines of code, on trains and stuff without internet, of course. Okay, so once again, if you're watching this and you're like, what the hell is this? What have we changed? You don't need to change anything. This is just for me. Yeah, this is just for me. So like Nicholas has pointed out, GCC will still give errors and things, but it doesn't give the nice explanations that DCC gives you. So DCC gives you the nice explanations. I can install DCC on my Mac. I'll do that for next week or something like that. Okay. Also, is this legible? I can zoom it in one more time if it's not. Let me know. All right. It's good. One more? Yeah, sure. There we go. Make that bigger, smaller actually. Something like this. Okay. All right. So we can print a linked list. We can create a node. What I think might be really nice to do now is to have a function that can create a node and add it to the end of the linked list. This is a common linked list function. Because at the moment, we're only able to create the nodes and add them to the start because we need to hook up the elements. So we're going to create a function. It's going to return a struct node pointer. It's going to be called insert at end. What data does it needs to accept? There's actually two ways to do it. You could pass in just the integer itself and then call malloc in the function. That's completely reasonable. Or you can pass in the already malloced new node. Does that make sense? So you could, that just depends where it is that you want to malloc it. Sorry, that's not true. This is the head pointer. Yeah. Yep, okay, semicolon here. All right, let's bring this down here. Print linked list, we'll do it underneath. You'll notice I probably am gonna be a bit faster with my typing because this is my usual environment. Okay, all right. So we've got a linked list. We need to think a bit here. We've got a linked list. Let's delete this. Let's delete this. It points to, we don't know basically where this pointer could be pointing to in the linked list. It could be pointing here. It could be pointing here. But the point is, that was unintentional, that I want to add a new node at the end. Right? So we want to take the final node that points to null, and instead of pointing to null, point to some new data. So what does that mean for us? So let's first of all write this here, a function to add a node at the end of a linked list. Yeah, I guess I'll sort of explain what we need to do. We get a pointer to a node. We need, yeah, exactly right, Elvin Seed. Yeah. I was trying to think of a nice way of sort of introducing it. But we just like our printing the linked list, we need to traverse to the end of it because we want to add it to the end. So we'll need to traverse the linked list, but we don't do anything, not doing anything as we traverse. We just want to get to the end. Does that make sense? And here I think this function is really useful for demonstrating the limitation of linked lists. Because to get somewhere, we need to traverse through each one. Even though I'm not even doing anything when I get there, but I need to follow the maze, right, to get to the end. But I mean, this is sort of nice because I can just copy this code. Whoops. I can just copy this code here. Right, this is all the same. This is all the same, but I'm not printing. I don't need to print. I just need to keep looping so that at this point here, now current is at the end because its next points to null because that's how the loop ended. Does that make sense? Shouldn't we pass in an int data? Yeah, I agree. We should actually. Yeah, we actually should. I'll add that to the end though. Good. Remind me in a second when I get that. Okay, so we traverse all the way to the end. That's fine. Now current is pointing to the end. So we need to make a new pointer, struct node new node. And if only we had some way to make a new node, and obviously we do, we have create node, and it handles calling malloc, setting up the data, setting up next, and returning it, etc., etc. So we can just call create node. It needs two things. It needs the data. So this is one of the nice things about Visual Studio Code. It actually looks at the function and tells me, oh, the function has two parameters. Here's what they are. And can you see here, It's looking at my comments that I wrote above the function and telling me what I wrote. So I can read that, oh, this function creates a new node. It returns a pointer to a node and its parameters, the data and the memory address of the next node. This is just my comment here. So you can see if you're a professional developer that this can help us be a little bit more proficient and effective. All right, so we need some data. For now, let's just put in the number 10. It doesn't matter. But you're right, we should pass it in and assign it. That would be cool. And then we need to pass in, what do we need to pass in? The memory address of the next node. What is the last element going to point to? What does the last element always point to in our linked list? This is the last element. It points to null. Exactly right. So that's what we're going to do here. Exactly right. Okay, but now we have a problem. Sort of, not really. It's not a problem. This is something else we need to do. The problem is, let's make this a bit bigger. We've made a new node. We gave it the value 10, and we set next to null. Do you see that? But now we have two of these elements. Like, we've created it, but it's not linked. It's not linked. And this element is still pointing to null. If you remember, current traversed all the way until it got to here. So current points to here, this points to nothing, and this exists, and I've just got new node, which points to this. Does that all make sense? This is how it's sort of currently set up. I've got a special null pointer here. So what do we need to do? Well, you can sort of see what we need to do. This needs to point to this. This will always point to this. That's fine. And this needs to, or the current actually doesn't really matter because we've already traversed. Do we need to assign current to new node? Careful, hippie hair. Rephrase that. You're so close. Well, actually, not really. Sorry, I've lied. It doesn't really matter if we assign current to new node because we'll be ending the function anyway. What do we actually need to change here? Which node? You'll see in a moment that it doesn't, we could do it, but it doesn't really matter. There's something more pressing that we're concerned about. Yeah, it's data 3, exactly. It's this one. This next should not point to null. It needs to point to new node. That's exact to new node or to this address here. That's exactly right. That's it. Whoops. So, but if we look back at Figma at our thing, current points to data 3. So what we can say is that the current next, which currently points to null, no longer should point to null. And what should it point to? Oh, I mean, Alvin Seed's just got it here. New node. Exactly right. That's exactly right. I never said here. Returns the... We've never actually defined what it should return. The address of the final I guess it should return the address of the final node. It could just return nothing. I don't know why. Yeah, this function might not need to return anything. It doesn't really matter, but the parameters are the pointer to the new, to the linked list to add to the end of, right? So what we need to, yeah, it doesn't really need, I'm just thinking, I don't think it needs to return anything. Or it could return the address of the new node. So it could return new node. I think that's also reasonable. The address of the final node. Yeah, that makes sense to me. Just because it might be useful to have that. It might be useful to have that. It might not. It depends on what you're doing. Okay, and that's actually it. How do we test that that worked? Well, we can call it here. Insert at the end. I need to insert our head pointer. And it's going to insert at the end. Then if I print it, it should be 1, 2, 3, 10. The benefit being that this will get constructed backwards because we didn't have this insert at end idea. And this will then be inserted at the end. So we should see 1, 2, 3, 10, if that all worked correctly. I compile it here. I've got some errors. Beautiful. Okay. Line 62. Oh, I didn't save it actually. Doesn't matter. There's still an error. Okay. Line 64. That's head pointer, not head. Thank you. That might be all it was. Yep. I think that's a nice spot. Okay. So I already compiled it. I run the program. There's an error. Fantastic. Some sort of segmentation fault. And this is where actually DCC might actually help us. But current points to head pointer. While current's not null, current is equal to current next. That's fine. That is not equal to null. Oh yeah, you're right. Yeah, you're right. I copied it from the other function. Yeah. The reason we need to do this is because we're trying to find the final element where the next pointer is null, not where it itself is null. So basically we want to do one less. We want to go one less. We want to find this node. We don't actually want to go to null and check that we are null. We want to check that next is null. Does that make sense? We run this and then we get exactly what we expected. 1, 2, 3, 10. When we were doing the traversal earlier, we didn't need to do anything. We were just printing the current value. So it didn't matter if we went right to the end. So Justin says, wait, how does it print the final data point whose address is null if the loop stops when the address is null? How does it print? Because it only prints, the difference between print linked list and the inserted end is that it only prints in the while loop. So it only prints if current is not null. If current is not null, then there's some data. When the while loop ends, it's at null. In this case, we're doing stuff after the loop finishes. Therefore, we want to make sure we don't loop one too many times where we follow to null and check that current. We never want to get to the point where current is null. So basically, Justin, to answer your question, we never do print the final data point address is not null. It's this address. Previously we were following to null and then we were saying, is this null? Okay, stop. Does that make sense? We actually followed it to null. Because remember, it is pointing to null, just like this is too. Oops. Yeah, no worries, Justin. No, it's good question. Tammy's just told me, should inserted end, I think Tammy's onto something here, return the head of the list instead. Otherwise, we can't cater for the edge case like adding one element into an empty list, as we no longer have a reference to head. Well, yeah, so Tammy's saying, should we return head here? We could do that, because we don't necessarily need to return the new node, because we could just traverse to get it again. It depends if the way you're using your linked list is to, if you store your reference to head yourself in the calling. So yeah, you could do that. We could also return the address of head so that we don't need to store it in the caller. Either work. Because remember, to get the final node, we could just traverse again to get the final node. And we could have a function called getFinalNode or something. That could be something we do next. But either way, this is going to work the same. Yeah, that's right. Yeah, thanks, yeah. All right. Any questions on inserted end? If we think it's helpful, I'll do a little poll here. Do we want to diagram out the insert at end function on the whiteboard? Alvin said, wouldn't it be better to have a dedicated struct to point to the head? A struct to point to the head. Yeah, you could do that. You can do that. That is how a lot of the linked lists are written. Both are valid. Okay, people want to see this on the whiteboard. Okay, all right, let's do that. All right, so let's reset everything. Like this. Let's do it like this. So this is at this point. You didn't get to vote. It's okay. It's like the federal elections, right? When it's skewed enough, you can stop voting. Okay. Stop counting. So we're at this point here. We've created the 3 elements and we've linked them up. I really got to stop doing that. So we created 3 elements, we linked them up, and then we have head pointer that points to data 1. Oh my god. Okay, there we go. Sorry for going a bit nuts there. We've got the 3 elements and we link them up. In fact, should we just do something like this? Too many things open. Exactly. All right. This should be okay, I think. All right. So then we call this. All right. Sorry. Bear with me. Then we call this insert at end function. So we jump down and we pass in head pointer. Head pointer is pointing to node 1. Do you see how this is all linked up sort of okay? So we jump down to insert at end. And this is the head pointer that we pass in. We make now this is not main anymore. So we're on a new stack frame here, which I could draw, or I could just rename this to insert at end. And we have this head pointer that came from the parameter. We make a new pointer called current. And current is assigned to head pointer. Head pointer points to data 1, so current is also going to point to data 1. Make sense? That's really annoying. Let's do it like that. Something like that. Whatever. So that's line 64. Tell me if I need to slow down or go, whatever. Probably not go faster. All right. Yeah, and of course, yeah, cool. Yeah, thank you, Tammy. Okay, that's line 64. Let's run line 65. While the current's next value is not null, let's break this down again. Well, current, and we're using that point, the arrow here, which means we're following the pointer and we're looking at next. Is next null? No. So it's not equal to null, which means we run the loop. And we say that current is now equal to current's next value. Next value, if we follow it, is this address. So current is now pointing to this address. Gotcha? Got me, I suppose. That's the end of the loop. That's all it did. We come back up to the while loop and we check it again. Is current, follow current, right? So follow current, is the next, which is here, is this null? Now, no, it's not null. It's this address here. Its next is null, but it itself is not null. So we assign current to be current next, whoops, which is to point to here. Right? Any problems so far? Let me know if it's okay as well. Give me some feedback, please. I'll answer your question in a second, Joel. Let me just finish up on this process. Is the silence? Okay, silence is good or bad silence? you gotta let me know. Okay, makes sense, says Cyril. I'll answer that question later, Green Machine. Good silence. All right, good. Okay. So we set current to do that. We go back and we check the condition again. Follow the current. Is the current's next null? Well, the current's next is null. Therefore, this condition returns false, and we don't run it, and we jump down to line 69. So this is what we roughly have. And maybe just to make this a bit nicer, I can do something like, it doesn't really matter where they are. Whatever. That's just maybe a bit cleaner. All right. So we're at now like line 68 or something. Line 69. Current is pointing to the final element. That's correct. We want to make a new node. This is happening in the function itself. So this new node, this call happens in the function itself. So we do make a new pointer called new node, and it gets assigned the result of create node. We can jump to create node, and remember it's calling malloc. So it makes a new struct of a node in the heap. That's the reason I'm showing you this. And it connects it. So we passed in 10 and null. So the data will be 10 and next will be null. And then we return the address of this malloc element, which means we assign that to new node. So new node now will point to this new node. Cool. That's line 69 complete. Now we have line 70 to do. And this is just to fix up, because at the moment our linked list is broken. We have item, link, item, link, item. It points to null. And remember, this next points to null as well. So it's something like this. Current.next should now equal new node. So current.next, which was null, now should be assigned to new node. What's new node? Well, new node points to this element. So if we assign it the same thing, currents next, right? And we have the arrow here, so we're following it. Currents next is now no longer null. It now points to what new node was pointing to. And this could just be, you know, we don't know what that'll be. 0 dot, whatever. And that's it. Then we return head pointer, which is this value here, so that we get a reference back to the start of the list. The function ends. Do we care what's happening here? Not really, because it all gets deleted when the function ends. And what do we have? A beautifully linked list. That looks a bit nicer. That's it. Fairly efficient. Yeah, that's right. We let it die. Exactly right. So we don't. That's what I meant by we don't need to point current here to here because we're just about to destroy it all anyway. And that is how we insert at the end. Yeah, the diagrams help a lot. Awesome. Good. Okay, what else can we do with linked lists? Sorry, could you just explain again how data 3 element changes and points to the data 10 element? We can actually just go back here. So at this point, we've just finished line 69. So we've created the node. And this is what we have. Something like this. Excuse me. It's line 70 that's doing this, Justin. So current points to the previous end of the list. We change its next, right, to point to wherever new node was pointing to. New node was pointing to the new node that we made. Therefore, we change next here, right? Current.next, this is that next here, to point to new node. New node points to this address. So it's this line that's doing it. You got it. Fantastic. Then the function ends, so we delete everything, including the stack frame. And we're left with our beautifully linked list with the fixed arrow. Cool. So Polkabra, completely understanding linked lists, has gone, okay, how do I get started? When's assignment 2 released? Assignment 2 is released at the end of this week, it should be. All right, so there's a lot of, yeah, calm down. All right, I can release it right now if you want. No. There's a lot of stuff we can do, you know, sort of functions and helper functions that can be useful. One of which might be, so something that's kind of useful is to have a function which returns an integer called size of linked list, right? Whoa. It just accepts the head pointer, right? And all its job will be is to traverse the list and keep count of how many times it had to traverse. You can imagine why this might be a useful function to have. So how we could do this in a few ways. I could just write it. Maybe I could leave this for something for you all to write because it's not too critical at the moment. What do you want to do? Do you want me? We could just. Do you think you get the idea for how to write something like this? Do you want to? I can leave it not done, and those of you who wanted something to practice on your own could try and implement it. You let me know. Leventier, what a nice name. Is that Italian? Random question. Has there ever been linked lists with the address of next and previous nodes? Well, great question. So that's called a doubly linked list, and absolutely they exist. Absolutely they're useful. All it is a node where you have the next and previous. Yeah. We don't cover them in 1511, but absolutely they exist. Cyril says, wouldn't it be more efficient to update the size whenever we insert or remove an element? Yes, if we always knew the size of the linked list. But it might be that it might be that we get given a fully formed linked list. Just like an array, there's actually no way to keep track of the size of it. So we could just go through and count it ourselves. Right? Think about it. Some other function could return to us a pointer to a linked list, and we have no idea how big it is. So if we could keep track of this, if we know for sure that we could always keep track of the size, maybe it would be more efficient. Yeah, it probably would be more efficient to just keep track of it, adding one each time we add. But even then, maybe not. You can imagine the case where you've got two linked lists and you want to add them together. What if you don't know the size of the other one? Something like that. So you need to traverse it and count it. But what do we want to do? Do you prefer me to write it? Or do you want to have the opportunity to write it yourself? Yeah. Leave for an exercise? Sure. I mean, it's a pretty simple function. It's a pretty simple... you're running right now. Cool. Yep. Maybe next week I can write it, or I'll already just write it so you can see if we did the same thing. But yeah, really, it shouldn't be too bad. Okay, I also realized that I didn't go through the slides, but really, I think basically I recreated the slides with Figma, right? So maybe these look a bit nicer, but I sort of did the same thing with the whiteboard. So I don't think we're really missing anything from these slides, but they're a good reference for you to have if you want to go through it in your own time. Printing out each node, that's exactly what we did. Maybe some slightly different variable names. This is a slightly different example that I don't think I'm going to do right now. I think there's other things we can do. Does anyone have any ideas in the last, not even, less than 10 minutes? 8 minutes or something, to write or to talk about or to ask or anything like that? Tammy or Noah, maybe some ideas for a function that's not going to take too long. Remove from the end or beginning. I like it. I like it. I like it. We could do that, absolutely. Let's do remove from the end. That's a bit easier. Let's do remove last node. I really like that one. All right. Yeah, remove last node. Yeah, or remove tail. Yeah, good. Is a nice one. All right, I'm going to sort of maybe do it a little bit faster. So this one is for you to try at home. Let's put this here. Let's put this here. All right. Well, a lot of this is going to be the same here because we want to keep track of it. We need to find the last node, so we need to traverse all the way to the last node. And get to the last node. So current will now be assigned. Current will now be, well, we don't really want to go to the last node. We actually, if we think about it, we want to go to this node and set its next to null, basically. So what we can do here, I don't know, there might be a few ways we can do this, but we can have, a separate variable to store the previous node. So they both start at head. That would be fine. The current, if the current x is null, current is equal to current.next, and previous is equal to current. I think that'll work. I mean, Tammy or Noah or someone in the chat can let me know if I've made a mistake here, but I think that's okay. So what this means here is that we should have current. Let me just make a new region. Oops. We have current, and we should have previous. We put them here. This starts, I mean, yeah, let's just sort of hand execute it to make sure my logic is right. Current points to head, which is the beginning of the list. Previous also points to head, which is the beginning of the list. While current next is not null, current is equal to next not null. Previous is equal to, no, that's not going to work, is it? Previous should be equal to, because if previous is now equal to current, or do we just flip it? Previous is equal to current. So at this point, we're like this. Previous should be equal to current. Current is this one. Then current is set to the next. Then we loop. Is the current next not null? That's correct. Previous will be equal to current. So previous will be equal to current, and current will go to the next. This looks right to me. We do it again. Previous will be equal to current. Current will be equal to next. Then current's next won't be null, and this will be where we end up when we're on line 83 or 84. And just to Elizabeth, yeah, I was unable to fix it, but today's lecture slides are actually 7.2 on the, they're just in the wrong order. So if you look at 7.2, that is today's lecture slides, and they're exactly the same. Okay, so we have something like this. What do we want to do? We're trying to remove the tail, which is this node here. So we can actually say previous dot next, not dot next, is equal to null, because previous is pointing to this. So this will change now to null. This will point to null. And actually, like, we've already done it at this point. However, as someone has mentioned, then we want to free current to make sure that we actually delete, we free the memory. And then the function ends anyway. What do we return? We could return nothing, or we could return the head pointer again. So I think this is one way of doing it. There's definitely others. We can test this here. We insert at the end, we print it, we can remove the end, and then if we print again, we should see it back to just being 1, 2, 3, if it all worked okay. Non-void function does not return. Oh, there's no return. Oh, is this one? Yeah, I'll just comment that out. So that worked okay. We run the program. Actually, and the other thing I might do here is in my print linked list function. After we loop, I can printf just a new line character. Just so it's a bit nicer. And then we go 1, 2, 3, 10. Then we delete it, the last node, and then we print and we just have 1, 2, 3. And that worked. I mean, that's it. So that's one way you could do it if you want to keep track of the previous and current. The other thing, I think... so Tammy has said in the other chat as well, alternatively loop to the second last element. But then would you be able to free it if we loop to the second last element? I guess you could just follow the next one more time. Yeah, you might be able to do it without... Yeah, I think you can do it without having these two pointers. But that could be something for you to try as well. Okay, well, it is 10:55 exactly. Yeah, that's right. And you could do that too. Yeah. And then to free it, you would just free current.next.next. Yeah, current.next, sorry. Yeah, exactly right. Yeah. That's probably a nicer solution because it's a bit less handling pointers. Yeah. But either work. This works as well. Because you're just storing some pointers. It's not too bad. All right, well, that's 10:55. Thank you all so much. Hopefully the pace of that was nice following assignment 1. Tomorrow we're just doing more linked list stuff. If you're playing along at home, right size of linked list. Maybe you fix up remove tail to be a bit clearer. Or to not need current and previous. Or second current or something like that. But thank you all so much. Oh, once again, before you all leave. Feedback, please, as always. I do read them all and I try and change things and all of that stuff. So thank you all so much. Congrats on finishing assignment 1. Congrats on your assignment 0 result. One more assignment and then we're done in the course. I mean, it's sad how fast it goes. But you're all doing amazing. Keep it up. Feedback. Look after yourselves. Have a good one. Bye, bye, bye.